Okay. So again, my apologies. Riemann-Roch is extremely abstract, but it's how it is. So I'm going to be as slow as I can, and but I can't give you intuition. If so far I could have given you intuition about these points and I couldn't relate them to something formally, here I can't do that even. Okay, you'll see what I mean. But if you really want to understand that, you need to know something about Riemann surfaces and differentials, and even that is not, the connection is not clear and takes a couple of hours to understand. And maybe one of you will do it in the seminar part of the course, but not now. So we are moving to the next unit of Adeles, and our aim is to prove the Riemann-Roch theorem. Okay, that's the point. We have 2 units for that, Adeles and differentials, and then the Riemann-Roch theorem. The proof is like one-liner given these 2, but okay. So a question maybe, if there are any questions. Yes. Yeah.
So in this sense, this shows that this construction of protocols is not like can't reach the optimum. Right?
Maybe that's the optimum.
Yeah, but the single bound.
Single bound is not the optimum. Maybe single bound is not the optimum. Who knows what's the right thing? So I should say this beats. I said that initially. This beats the probabilistic method. Single bound is a lower bound, like an impossibility result. So no one knows what's the right answer. You can slightly improve that, by the way, actually weirdly, using the infinities. If you allow the infinity as a symbol, you can actually improve that a little bit using the same code, but just using infinities. Think of them as a natural symbol. Then you improve it slightly. So this is really not optimal, but only slightly. And no one knows. That's a huge question. What's the right answer? No one knows it for any value of q. Not 2, not 3, not 4. Only for n. Like when q is n, single bound is tight. When q is 2, it's a huge problem, like in coding theory, like open for 70 whatever years, understanding what's the right distance trade-off that you can have. This could be optimal. This surprised people because they thought this can be possible. Right. If you allow q to grow, then I don't know when is q large enough so that we know everything. When q is n, it's fine. Maybe when q is square root of n, it's fine. I don't know. It's like a weird regime. If q is square root of n, it's just n already. No one cares. So I don't know. Maybe if q is log n or something. Next weird things happen that you can, a billion groups are okay. I don't know. So, but maybe that's optimal. That could be optimal. That would be amazing to prove. Like, yeah, I don't think no one actually tried. It's like so far away from what we know how to do. So, I mean, I'm certain that like my goals are much more modest. Okay. So here's the definition for you. So an Adele, it's like I think it's a small wave or something. Okay. Adva. Okay, I'm not sure. Adele, but it's going to be apparent in the definition of a function field. So it's a new creature that we are introducing. Is a map, usually denoted by alpha or beta or something like that, the small Greek letters, from the prime divisors, not just rational, all prime divisors to the field. Right, so essentially it's a function. It takes a prime divisor and put a function there. Right, a divisor takes a prime divisor and puts a number there. Here you take a prime divisor, which you think of as a point, and put a function there. Very weird. Like you have the curve, and for every point you have a different function. It's like a weird mix of local and global kind of stuff. Like it's local in the sense that you have points there and you talk about them, but you are not restricted by any means. You can put any function you want at any point, except, but satisfying that, at every point you can put a function, but almost always, namely except for finitely many prime divisors, the function that you put should be defined at the point. Right, so the picture is like, this is the curve, and for every point you have a function. The function here is alpha of p. Right. No, it's like looks like it's something that's going to eat something, right? Anyhow, So, so you can put any function you want. So it's like a global definition. It's not restricted by the curve, but you do require that. But for finitely many points, every function is defined at the point which it sits at. It's like a very weird definition. You see that someone thought long and hard before defining it, right? It's like a mix of global and local requirements. So, which is really hard to justify unless you see what we are going to see. So the proofs, the algebra, these are called, so these are, I think this was introduced by Vail, if I'm not incorrect, probably incorrect, but definitely by the algebraists, and it's not like the first thing you'll do. So some remarks about this definition though, before going to break. So first of all, just as a notation, technically you should write alpha p, but you write it alpha sub p. Just because it would be nicer not to think of it as a function, because you have functions over that, and then it looks like functions of a function of a function. So we write alpha sub p for alpha p. The set of all Adeles of a function field is denoted like this cool, like that. And if you want, you can put the function field here. Okay, but you usually don't. And what I claim is that it's a ring with pointwise, with the usual, it's like a function. So with pointwise addition and multiplication, like the usual thing, how you usually do, right? So if you have two Adeles, then you can define their product Adele, which at point P is alpha P times beta P. And you just need to make sure that finitely many places are, the functions there are ill-defined, but that's fine, take the union. And same for sum. That's an Adele. Also, this thing is also an Adele. Right? Some more non-trivial remarks. Oh, good. Yeah. Don't worry, we are going to cover those. But the zero is the zero. Right, the zero is the zero Adele, right? So the zero function everywhere, and the zero function is fine because it's always defined, so it's fair. And one is, I think, the function one, which is always the Adele which always have one. I think it's fine, right? Because when you get one at P is P, and it's always defined. Right. So that's what I want to say now. So you can take a function and make an Adele out of it, like the constant Adele that always output the function, and then the 0 and the 1 or the 0 and the 1. So another thing, why did I? If I already did it, so. Yeah. So another thing is that we identify, exactly, F as even a subfield, not just a subring, because it's a field of A, right? So an element X, so this is an element X in the field, so you can think of it as an Adele. So we're never going to write the brackets, we're just going to write X, but just for now, we can take an Adele, which just outputs X all the time, right? So, sorry? Wrong A. Oh, thanks. Like that or something. Yeah, what was that?
It's like the constant Adele.
Right, it's like the constant functions, constant Adeles, right, exactly. It's right. So that's funny because you output a function all the time, which is not necessarily constant. But by the way, it's fine because every function has finitely many poles, so it's an Adele. Right? And also, okay, also, so kind of more than that. So you can, the proper name is an F algebra, but I don't want to use this name. So you can actually, so with that, you can multiply. So because we identify F as a subset of the Adeles, and we know how to multiply Adeles, we can now multiply a function with an Adele. Just think of it as an Adele and multiply. But really what it means is just multiply the function at every point, right? So just to make it explicit, so we define x times alpha, where this the evaluation, like the evaluation symbol, VP from F to A. Right, so VP, it already has two parts. VP of a function is, how many poles or zero it has. VP of a divisor is an extractor procedure, taking the number. And VP of an Adele, now a new thing, is, how would you define it? Like, what would you do? Exactly. Right, so you go to alpha. At point P, you have a function, alpha P. So the valuation of the P valuation at alpha is the P valuation of that function. Very weird, but, if you insist on defining it, that's how you should. Yeah, it's a local information, right? But VP tends to have this, so that's fine. Good, so after the break, we're going to continue studying Adeles and enjoying them. Good. So first of all, just recall, right? So if you have a divisor, then we define the Riemann-Roch space of a divisor, right? Before we talked about Adeles. I just want to put it here as a comparison for what's coming. Right, so this was the Riemann-Roch space, all functions, such that they kind of satisfy the requirements coming from the divisor. And I want to define Riemann-Roch space for Adeles, because it also has functions. So we are going to define lambda A, lambda is like L, lambda A is all Adeles such that, and then I'm going to write the same thing, but replacing X with alpha. Same definition. But here you have more freedom, much more freedom, right? Here you fix your function, and then that function has to satisfy everything from the divisor. And Adele has the freedom of choosing a function at every point, except for the fact that it should almost always be, defined. But other than that, it has much more freedom, and so this thing is much larger than that. It includes that as a subspace, as a subset. Yes.
Alpha in A, that the image of alpha is in LA? Like, is it equivalent?
Image of alpha? What is image of alpha?
Like what function?
But for different points? No.
Not sure.
Yeah, no, I don't think so. Yeah. Okay, but what you can say, I don't think it compiles in my mind. But what you can say is in two other things. So first of all, this is for every A, every divisor, this is a K vector space, like a Riemann-Roch space. So Riemann-Roch spaces are vector spaces over K and also these. Right, if you take an alpha and a beta, and you have this for alpha and you have this for beta, you have this for alpha and beta, because it's like a pointwise thing, because it works for functions. Right, how you show it, you show that for every P something happens. But for every P you have a function there, and you don't look at the other functions. So it's the same proof as that. This proving anything about this thing is like point by point. So that's true. And the zero is the zero Adele, so forth. And how can you get the Riemann-Roch space? Let's call it the L space. What is the relation between the L space and the lambda space? Exactly. So do this, right? F are the constant Adeles. Like by writing this, I mean, I think of the functions as Adeles, and right. So and back and like I don't imagine the difference even. So for me, a function is an Adele, and so right. So all functions that satisfies the requirements are exactly those. It's like almost a tautology once you identify f with a, with the embedding of it in a. These are all functions that satisfies all the requirements. So this is precisely what's written. Good. Yeah. So if you want a picture, I don't know what this picture is good for, by the way. I don't think I use it, but I think I draw them for myself. Like, but let's draw the picture. So if you want a picture, then you have like, you have K, and then you have LA for a given divisor, and LA is contained in the lambda A. Now these are Adeles, and in the entire function, like this is a subset of these, and it's actually the intersection. When you write something like that, you mean intersection. Okay. And then this is contained in their sum, which you may not thought of taking because it's maybe weird for you. But these are just vector spaces over K, and all of this lives in all of the Adeles. Sorry, I don't have a room. It's fine. Yeah, LA is part of. Right, so all Adeles contain all of these things. This is like thinking of this as Adeles. It's a K vector space, the embedding of F. And this is some of the Adeles, depending on A. And right, and you have this diagram, which I'm not going to use. I just draw it for some reason. It's nice to have. It set things. I don't know, set the stage, I think. So far we don't see why we care about Adeles. I just define them. It's weird. I know it's weird. But what I'm going to do is to state 3 things about them and prove all of them in the video. Yes.
We identify the element in F by the constant Adele, right?
Yeah. Every element in F is in LA, but LA is not Adeles, are functions. This is the Riemann-Roch space. No, because lambda has constraints. I mean, lambda is all Adeles such that something happens, and here you are required to take the constant function. So nothing is contained in the other generally, because maybe the constant function, maybe the function that you take here is not satisfied by A. Yeah, exactly. That's why this equality holds. Yeah, right. So I'm going to state a claim. That's an easy claim, really. It's not. I'm not going to prove it. No one ever proved it. But then I'm going to state 2 results, which are not easy, and I have them in the video. Okay. So yeah. So if you have 2 divisors, A and B, then if A, so if A is smaller or equal than B, then what can you say about the lambda spaces of the corresponding divisors? I think it's like in Riemann-Roch spaces, right? Because when a divisor is large, you allow more. Like think of degree R polynomials. When degree is large. No, because when the divisor is larger, it's easier to right. Maybe I think positive is good. So always have in mind the L of R times P infinity. When you increase R, there are more things there. Right? There are more polynomials. Right? No. Right. It's, yeah. Right. So it's not like I know what you mean, but it's not like that. It's yeah. So if a number was when you increase, you may take a negative number to a positive number even. Anyhow, that's what it is. It's just going to confuse everyone. So what do you think? Now these are harder questions, but let's try them. So if you take the intersection of 2 lambda spaces of Adeles, and I insist of writing it as a lambda space of another divisor. So what divisor should you take? Very good. Wow, that was quick. Right, I mean, we know that will decrease the sizes because we said it. This is smaller. It decrease, And also that increases the size, so maybe that's the right answer, and that's the right answer. It's really obvious if you just play around with the definition. You require this and require that, so you require this, which require both, because minimum is smaller between them.
Like a point where
A minimum was defined when talking about divisors. It's point words here. No. And what can you say about, okay, actually ask a harder question, if you don't mind, because I see that you somehow guess it right. So what should you do to the subspaces in order to get the max sum? Right, there's nothing there. Yeah, good. And it's also easy. That may be slightly harder. That's tautology, and that's you need to do a little bit. But okay. And then what can you do? What happens if you move, right? X is an element in F. Now, right? We know that X times the Riemann Roch space of A is another Riemann Roch space. Here it's like this is a bigger field. It lives somewhere, but it still have K vector space. It lives in the Adeles, not just functions. But what do you think? The same thing will happen or not? Exactly. Good. It's the same thing. There was a minus there as well. And that's easy. These are easy claims, really. I mean, that's slightly harder, but all of them are easy, and you can, but are not advised to prove them. Just look at them and feel them, and then you're fine. The things that are not easy are going to state two lemmas. I'm not going to prove them. They will take 45 minutes to prove. I proved them in the video, and it took 25 minutes. So that's why I know it will take 45 minutes here. And I'll upload them, and you should see them if you want. But these are I have to somehow skip things, and these are things that you can skip, and it's worth skipping. Or actually, so maybe before, as a reminder, I mean, I prefer to kind of delve on the conceptual, to some extent, part than the formal part, technical part. So remember that if you have two divisors A smaller or equal than B, then we know that the difference between dimensions is at most a degree difference. I could prove that last time. And that's the monotonicity really, because this is the difference between dimensions, and if you move things around, you get that deg A minus the dim A is at most deg B minus dim B, which we use today. So we know that, and we also know that there is an equality. If S, I mean, there is a version of it which is with equality, which you proved before and then deduced that. So we also know that if you take the truncated, which I don't want to look at too much, right? Where S is the support of A and B, the joint support, the union of the supports. I never actually defined that, but you know what I mean, the places where you get non-zeros. Then this is equal to degree minus degree difference, degree of B minus degree of A. Right, so this is good, but this is bad. We don't want to look at that. And that's good, but that's bad. So I want to enjoy both. I want to find some natural object. I don't think of this as natural. A natural algebraic object that encodes the degree difference. And that's why we have Adeles. So I wonder if it was a reverse engineering of sorts when they did it. So the lemma 5 will tell you, which is proved in the, I'm going to upload to the videos, to the YouTube. So if you have two divisors like that, then if you look at the quotient of these K vector spaces, the lambda vector spaces, not the L vector spaces, but you see there is no weird S going on here. I don't know, I prefer this over that, that's what I'm saying, for the rest of the development. That does equal to the degree of B minus the degree of A. Okay? The proof is obtained by showing an isomorphism between this and that. And I'm doing it in the video. But so you need that. But that's the better way of explaining the degree difference. Okay, so no proof today. And the second lemma, which uses that to get it, tells you that there is another algebraic object related to Adeles that encodes the deficiency difference, not the degree difference, the deficiency difference, where deficiency is degree minus dimension. So the dimension okay, so let me just write it. Okay, so this is a natural parameter. This is the deficiency that we talked about. So it turns out, and that's why we prefer Adeles, they behave better. It turns out that if you add to the Adele space F, right, both of them are K subspaces of A, so you kind of add all constant functions here. And now you take the quotient, and you can, right, this is a subspace of that. Then what you encode is the deficiency difference. This is requires, I really like this proof because it's like, it uses twice the second isomorphism theorem and once the third, given that. So there is a proof by picture, which I didn't print to save paper, but anyhow, proof by picture, which I'm doing in the video, it's like a 2-minute proof, but you need to have the right picture, and then you need to justify it with another 7 minutes. But anyhow, if you have time, you should look at those proofs, but otherwise, our time, is limited, so let's take them as granted. Yes. Good. But as a corollary, so that's all what we are not going to prove. Let's prove things. As a corollary of that, and again, I wish I could have proven it, but last time I gave this course, it was with slides, and then the pace was like really fast, and we proved everything, like the opposite of what I'm doing here, and of what I'm starting to do here. And I think this is better. I think it's better to just take this and think about them later, and not do it quickly, and it's in the video so you can see it. And it's actually slower in the video in a sense because you can kind of stop and think about it. It's like easier to follow a video than I think a human being like live because you can't stop me all the time and you can stop me there. Yeah. Anyhow, you can stop me here also, but there it's like maybe you feel better. I don't know. Okay. Stop me, please. Yeah, okay. So the corollary is okay. So if you remember, this deficiency only increases as A increases, right? That's the monotonicity. And it cannot exceed G minus 1. G minus 1 is the largest deficiency. So what this corollary tells you that if you take a divisor that maximizes the deficiency, so it's a large divisor in a sense, then it's large also in this sense. Namely, it's kind of amazing. Lambda of A, which I think of it as kind of small, plus F, which is very small, only constant function, gives you all possible Adeles. So A is because of that, when A is maximizes the deficiency, lambda A essentially all the elements in the Adeles are lambda A plus a constant. That's how you should think of it. Let's prove this just to get used to the definitions. We're just going to use it as or something. But okay. So as a starter, let's take any divisor B larger than A. When by monotonicity we know that degree of B minus dimension of B is at least the degree of A minus dimension of A by monotonicity, and this is G minus 1 by definition, and this is what? What can you say about the upper bound on that? Right, it's as small as G minus 1, because G minus 1 is like the largest possible. So really it's G minus 1. So this means that, right, so this means that any divisor. It holds for all the monotonicity holds always. Right. And also the upper bound is by definition of the genus. We proved that in Riemann theorem, we proved that this upper bound, so once you fix an X, and the bound on MX is a bound actually for all divisors. Right. Right. So so what do you know? You know that this difference, that minus that is 0. You know that they're the same. So if you look here, then the dimension of this quotient with this notation is 0. It's the difference between is 0. So this means that this equals that. So lambda b plus f is lambda a plus f. So this is lemma 6. And it already gives you kind of, A is very large, because take any larger divisor than it. It won't give you more functions, right? So whatever you can do in lambda b plus lambda a plus f, you can already have done with lambda a plus f. Just because the quotient is going to be 0, it's the same thing. Okay, so that's generally speaking. Now I want to address the alpha that I don't see here. Ah, yeah, good. So now I want to prove this. So obviously, I mean, the inclusion in this direction is obvious by definition. So I left with that inclusion. So I'm taking alpha in A, and I want to show I can write it in lambda a plus f. So take alpha in A, and let's choose, so that was for any B, larger than A. And choose B larger than A, so I can use this, such that for every P in P, VP of B plus VP of alpha is non-zero. Right, so you gave me an Adele, and I want to find a divisor that both beats A and that beats the number of constraints I have, the constraints I have from the Adele. Now there are infinitely many constraints in the Adele, but only finitely many of them are negative. Right, because in the Adele, only for finitely many points, you have a function that's not defined there, which means negative numbers. So this thing, which has, for every P, this could be many numbers. All of them are either positive or 0, but for few of them which are negative. And so I only have, when I construct B, I only have to worry about some constant number, finite number of negative numbers to worry about. So there is such a divisor. Divisor should have a finite support. So the richest, sorry? Right, exactly. And then take the max with A. So I can do that and that, or take exactly, I can take exactly. So this means that alpha is in lambda B. Like that's another way of saying alpha is in lambda B by definition. Usually just write this before that, but it's lambda B, which is contained in lambda A plus F because of what we did before. Because of this thing. Yeah. So kind of, again, I'm proving stuff that are kind of abstract, but there is some intuition to that. When the divisor is large, in this sense, it's large in that sense. So when the numbers that encode the divisor are large, then you can actually, you can span every Adele using Adeles from here plus a constant. And corollary, the last corollary, actually it's nice, says for every divisor A. Again, this is why we like Adeles. If you look at all of the Adeles, all of them, and divide by lambda A plus F, which is like a star in the show, then it encodes the deficiency of the deficiency. That's what I wanted to say. Right, so this is the deficiency of A. G minus 1 is the largest possible deficiency. Oh, there's a G minus 1. Let's see in the proof in a second, but that's fine. So this, the G minus 1 was the maximum. Yeah. No, this thing can be at most G minus 1. You can't make it. You can't take this to be one thing and that to another thing. So what I'm saying is that this is the deficiency of A. Do you agree with that? This is the maximal possible deficiency ever. So the difference is a number between 0, it can be smaller than 0. And what I'm saying is that this number is encoded by the dimension of all Adeles over there. Okay, so let's do the proof. Right, so 0 is always there, you see. So right, so the size of it is 1 because 0 is there, but its dimension is 0. Right, yeah, that's something else, right? But in k-vector spaces, right? Good, yes. Right, so there is a picture, but yeah. Okay, let's do the proof first. Where is the proof? Thank God. So no, it's really easy. So take any. I mean, the real magic happened in the lemmas I'm not proving. So, that's why these are corollaries. So we take any b that's larger or equal than a, when we know that, and take it larger or equal such that it has a maximum deficiency. Right? You can do that. You can take any divisor that attains the maximum, and then max it with a, and it's even larger, so efficiency doesn't decrease, and you're fine. Right, so you can do that. And now by corollary 7, which is here, which is not everywhere, it's here, thanks. What do we know? We know that, okay. So corollary, I think I need that also. So corollary 7 tell you that lambda a plus f is a, but this is with b now, so maybe let me write down. So the dimension as a k-vector space, of course, of a over lambda a plus f, that's what I'm interested in here, by this thing. Now a I can replace with lambda a plus b, lambda b plus f. Right, because the corollary 7, because b has maximal deficiency, all Adeles, you can replace all Adeles with this thing, lambda b plus f. Good, and by lemma 6, now you see the degree differences, deficiency differences. So it's g minus 1 minus deg a minus dim a. G minus 1 is the deficiency of b minus the deficiency of a. This is a 6. And using that. Yeah, and that's it. So the picture, if you want to have a picture, I mean, just to appreciate it, now we would have finished lemma 5. So think of a parallel world where you're seeing the proof of lemma 5 now. So the picture is you have a. I think it's the same. That's why I see. It makes sense only afterward. So that was the picture from before. Right, you have k, like f5, L of a, lambda a, f, sum. And then all Adeles, this was like very small the first time I pictured it. And this captures the deficiency, like the deficiency of the deficiency, right? Which should be good, right? So, okay, that's what we just proved. Questions about that? Yeah, I know what you're thinking. You're thinking like, probably you're thinking when this is going to over, but you're thinking like, what is going on here? Like, what are we trying to do? Like, what's? But you see, at least we found algebraic structures that encodes things that we care about, like the degree differences and the deficiency differences and the deficiency of deficiency differences. And you can't work with numbers, you can work with structures. So now we try to understand the structures to better understand the numbers. That's what's happening really. Numbers are shadows of something, and we understand the something now.